Okay, it's once again physics colloquium time. So, if you are here for the Biology 400 review session that was scheduled in this room, it's now in 2001 the lot. So I apologize for the little scheduling snafu. It gives me great pleasure to introduce our colloquium speaker today, Professor Caballero from Michigan State. He got his undergraduate degree from the University of Texas, went on to Georgia Tech to get his graduate degree. It was the first physics education graduate degree from Georgia Tech, is that correct? Yeah. Then went on to do a postdoc at the University of Colorado before joining the faculty at Michigan State. He is an internationally recognized expert in physics education research with a particular interest on computation. So please join me in welcoming Professor Caballero.
So thanks, Chris. Thank you all for inviting me today. I'm excited to share with you some of the work that I've been working on with folks at Michigan State and elsewhere. Sort of before I do that, I want to tell you a little bit about who I am and sort of where I come from, because I think that these introductions often emphasize parts of our histories that are sort of very formal, and also sort of emphasize like the academic side of things a bit. So I grew up here in South Texas in a little town called Mission, which you probably never heard of. There's no reason for you to have heard of it. But if you've ever had a ruby red grapefruit, that's actually where I grew up, is where those are grown. And so this is not my trailer, but there are trailers like it, and that's where I grew up, basically across the street from these grapefruit farms. My family were farmers. We didn't really have a history of college in our lives, right? That was not part of our familial history. But I was fortunate enough to go to the University of Texas after finishing high school. Not having that history was kind of important and pretty formative, because I spent a lot of time not in classes. I spent a lot more time doing this, because Austin is an incredible place to live and spend time. So I basically dropped out of college for a little while and was trying to figure things out. Decided that I really didn't like doing all of this stuff all of the time, and that I could sort of partition that a bit. And so I went back to school, got my bachelor's degree in physics, and then had absolutely no idea what I was doing after that. So I applied to graduate school. I didn't get in anywhere. I ended up applying to pyrotechnic school, which the best pyrotechnic school is actually in Central Florida, which makes a lot of sense, because that's where all of the amusement parks are. So I was about to go there, and then I went to the bar and saw a friend of mine, and he said that he got into Georgia Tech and they were still accepting students. So I immediately called my academic advisor. I was fortunate enough to get into tech as a result of sort of late admissions. I spent most of my time doing this. Actually, the first experiment I worked on was watching paint dry. That is not a joke. That is literally what we did. This is some pilot wave dynamics, where we sort of trained a droplet to interact with this spot here, which is actually a pulsed laser. And then you could move it around, and the droplet would move around and so forth. I got pretty bored with that because I didn't really see much of a future in doing this. It didn't really make the impact that I wanted. And so I switched to doing education research after a long conversation with my PhD advisor. I graduated some years ago with that, and then went to Colorado, did a postdoc, and now I've been at Michigan State 7 years, and got tenure a couple years ago. So that's the story. If you have questions about it, I'm happy to answer them later. But let's get into the actual reason that I was invited here. So I'm going to tell you a little bit about the work we've been doing around introducing numerical computation into physics courses. And I'll tell you mostly about research, but there is some sort of programmatic stuff that we can talk about throughout. And I should say, if you have questions or comments, please just blurt them out, raise your hand, do whatever you need to do to get my attention, because I talk quickly and I might not pay as much attention as I should. Before we dive in, I want to acknowledge the research group that I work with. So this is the current list of folks that work in our research group. We have 5 faculty, a lot of postdocs, undergrads, grad students. It's a pretty good-sized physics education group. The reason I start with this slide is to acknowledge that I have the privilege of talking to you today. Right, y'all invited me and not able to invite the whole group to come talk to you, but I represent the work that we are all doing. And so my job is to best represent that work and not take ownership over it. So as you start to see, names will pop up here and there. there, these are the people that are actually working on these projects. I'm fortunate enough to be able to work with them and to advise some of them. So just like y'all's physics department, ours has two very sort of big high-level goals. One is conducting original research, really trying to sort of push forward our understanding of the physical world. And the other one is educating the next generation of students. This photo here is actually from the National Superconducting Cyclotron Laboratory. This is my, one of my students that I work with, Alea. She and I have a service project with some other students working on physics education in Ghana. If you're interested in that, I can tell you about that later. This are photos from my colleague Vashti Sautel's introductory physics for the life science class, where students are doing some momentum conservation experiments and some electrostatics experiments. So my work connects these two things. Fortunately, I get to do research that supports education. That's the main part of my work, and that's sort of the premise behind it all. And our field is pretty broad. It studies lots of things. Obviously, student learning and engagement is a big part of it. Pedagogy and curriculum, recruiting and retaining students in the major. We study issues of diversity and inclusivity in physics, faculty practice, department culture, et cetera, right? So national landscapes and so forth, right? Lots of different things, not just about learning, not just about classrooms. Lots of stuff happens. And we contend with some pretty large problems in physics. Student learning, as we've observed it over many years, is improved when students work together and we use these sort of called evidence-based techniques, helping departments adopt these, helping faculty learn facility with them, sort of looking at the actual impact of those things. That's a really big part of what we do. If we look at the participation in physics, it's not really kept pace with the rest of STEM. Biology, chemistry have continued to grow. We've started to grow again a little bit, but we haven't really kept pace. This is more of an observation, not necessarily arguing for more physics majors, but rather something that's interesting. Women and students of color are significantly underrepresented in physics departments. That's at the undergraduate and the graduate level, as well as at the faculty level. The year that I graduated with my PhD, which was 2011, there were 11 other students of Hispanic heritage that graduated with their PhDs. That compares to about 6,000 PhDs granted across the United States, right? Now, physics is also changing, and it's been changing for a long time. We use a lot of new tools, we use a lot of new techniques. This is sort of where my work is situated mostly, is trying to understand how we might incorporate this thing into our classes a bit more. Right? That we actually represent the physics that is being done now in this way. So this thing's done a lot for physics. I'm going to just show you some high-level examples, ones that I could find on the New York Times webpage, which means that everybody is actually probably familiar with them. Right? So here's a picture from the New York Times webpage some years ago. This is a picture of the auditorium at CERN. People are super excited. They're super excited because of this bump. Right? Now, I don't want to dismiss like the amount of experimental work that's necessary to do this kind of science. It's really, really important. But the numerical work that's needed to be done, and people here probably know that much better than I do, is pretty incredible. My understanding of this is that data comes out of this so quickly that it can't be written to disk. You have to actually make decisions on the fly and decide whether you're going to keep that data around and do more analysis. Like that's, to me, is incredible. For some reason, if you search for the first chirp on the New York Times website, you can't get a pretty picture. So this is the second chirp. Here, I mean, you all know about this, right? So here's the data from this situation, right? We're talking about this black hole merger ring down. And this kind of analysis, this kind of data, again, not to dismiss the experimental work, but the numerical work needed to model this is pretty incredible. Somebody once told me, and I'm not sure that I fully believe them, but I'll go ahead and repeat what they said. That strain measurement is 10 to the minus 21. And what was told to me was that that is the same as the distance across your thumb compared to us and the next closest galaxy. That's sort of the resolution there. Now, I don't know if that's true. Don't fact check me. All right. Moving on. So what I'm saying is that computation is how we do modern science, right? It's a very important part of what we do. This is the stool metaphor for folks who, sort of follow some of the work that's being done by AAPT in computation. That theory, experiment, and computation sort of support this modern work. I don't necessarily think of these as distinct. They're actually quite blended together, but this is just a nice picture, right? We can ask the question, though, what's changed in physics education? We've seen this massive change around computation being incorporated more into physics research. It's helped drive a lot of discovery. It's helped drive a lot of technology. But we can ask now, all right, well, what's going on with physics education, right? So let's zoom back to the 1860s, 1880s. We have this sort of description of Maxwell's equations sort of written in much more modern terms and how it's represented in textbooks. This was sort of a really important understanding at the time. We can go back and we can look at a physics textbook that was used in an introductory course. And you see here is the Atwood's machine, right? And so, you all know the game, right? There's a mass on either side, there's a rope over a pulley, and the game is to sort of model the motion of the, yeah? Okay. This seems maybe important at the time because people were moving heavy objects around manually, I guess. You could add more pulleys, you get some mechanical advantage, maybe all of that's kind of important. Sure. All right, so let's go a little farther forward. We have the sort of development of the special theory of relativity. We have sort of the photoelectric effects, so we start to describe quantum mechanical systems and so forth. We can go and we can look at an introductory physics textbook, and we have the Atwood's machine from a German military manual right around 1910. Interesting. So a lot more detail. It's very pretty. It's shaded, which is cool. All right, so let's zoom a little farther forward. You have the development of radar, right? The development of the laser. We go and we look at an introductory physics textbook, and there's the Atwood's machine again. I think you get where I'm going with this, right? All right, so in the 70s and 80s, right, we have nuclear energy. We have the development of the personal computer, which fundamentally revolutionizes how we do science, so much so that we can draw the Atwood's machine with the computer. This is when I was in college, so we have these interconnected devices that talk to each other, and they allow us to do both really important and really stupid things. We have computers in our pockets now. Books don't need to be printed anymore. So now the Atwood's machine can be in color because it just exists on the web, right? But the point being is that, this is a bit tongue-in-cheek, but our introductory physics courses, and I think if you look at all of our physics courses, right? They really haven't changed very much, particularly since the 1950s or so, maybe the 1960s when we introduced calculus. And so there's a question there about, well, what should we do? And I think my argument for this whole talk is basically a physics education requires a computational education. It's how we prepare people for the 21st century and for doing 21st century science. So here's a picture of a formula sheet from a quantum mechanics class. And you can see that it's very neatly written. All the subscripts are there and the superscripts, and it's even cordoned off with little like blue lines to indicate the only stuff that needs to be paid attention to for particular problems that show up on the final exam, right? And this is oftentimes, this is a particularly egregious example, but this is what we often see students leaving courses thinking physics is, right? It's this collection of equations that sort of partition off and describe certain systems, and that's really all I need to know. Whereas the understanding and the underlying sort of relationships that led to those equations that lead to sort of connections across these boundaries, like those are like the really important parts of physics. And I'm not saying that computation is some silver bullet that will handle this, but this seems particularly problematic and something that we probably don't want. Additionally, you have this sort of affordance of visualization, right? So here's some models of particles in a square well and a harmonic well, sort of showing you what's going on with the probability distribution. In addition, computation allows you to sort of generalize your problem solving to different kinds of problems that all are described by the same kind of situation. So this one-dimensional differential equation can describe the buckling of a beam. It can describe the potential between two plates. Well, it can describe a model for diffusion, depending on how you choose A and B. But the numerical process for solving the problem is the same, right? And so we get this sort of maybe ability to generalize our tools to a variety of contexts. Okay. Now, in addition, AIP, which is the American Institute of Physics, collects a lot of data around this kind of stuff. And one of their surveys, which is now a bit old, so they're probably going to redo it pretty soon. They ask, where do bachelor students who earn a physics degree go? What do they do, right? And about half of them or so go to graduate school, mostly in STEM, right? So they're going into engineering and physics, astronomy, so forth, right? And so they're doing modeling, simulation, data analysis, all of those important things that sort of computation helps support. But the other half are going into the workforce. And this actually varies by school. So this is a national average, right? So, Yale's sending 99% of their students to graduate school, probably, I don't know. Georgia Tech is sending close to about 50%. Michigan State actually only sends about 25%, right? So a lot of our students are going into the workforce. When you look at where in the workforce they're going, most of them are going into STEM jobs, which are characterized by jobs that have modeling and simulation and data analysis as part of them. They're working in engineering firms, they're working in design firms, they're working as analysts for IT companies and so forth, right? They're doing a lot of this STEM work that is facilitated by a computer. And so, at least at State, the vast majority of our students would be best served by having some understanding of computing throughout their major, because they're both going into these graduate programs and going into STEM jobs, right? Okay, so you might ask the question then, well, how do you go about integrating this into your courses, right? I have an answer for you, but you're not going to like it. So this is a paraphrased conversation at a large Midwestern university. Okay, so Professor 1 says, I want the students to use computers to solve interesting problems. Professor 2 says, then have them code. Professor 1 says, this isn't a CS class. Then Professor 2 says, then don't have them code. Professor 1 says, then I can't have them do the interesting problems. Right? This is a series of circular arguments that occurred at this large Midwestern university, some of them in committee meetings, some of them in faculty meetings, over a number of years. So the answer is basically it's complicated. It depends on a wide variety of things, including your sort of interdepartmental dynamics and resources and so forth, right? So that's the punchline. If you leave with anything today, the answer is it's complicated. But we have models for this. We have models for understanding why this works the way that it does. So we all work at a university, right? And inside of that university is the physics department, which has a certain relationship with the college, has certain resources that it can get from the college, it has certain expectations on it, etc. Within that department, we offer physics courses. There's some expectation about what those courses look like, how they're structured, what kinds of resources are allocated to it, who teaches them, how often, etc. Within those courses, there are class meetings. They occur in particular kinds of rooms that have certain structures. You have certain allocations for those meetings, how long that they meet, etc. You have certain activities that you can do in that class depending on who's in front of you, what they're expecting of you, what's graded, what's ungraded. And you have specific tasks that are within those activities, that may have some particular challenges associated with them depending on the content themselves, what you're asking students to do, what resources are available for you to support the students, etc. And sort of all of these layers of this problem are sort of interconnected, right? Because they all talk to each other and they all sort of interact with each other. And so the way that our group approaches these kinds of problems is to think about these sort of different layers and to try to understand, well, what's going on across these different layers, and what is it about some places that are doing this versus other places, for example, or what is it about certain kinds of tasks versus other kinds of tasks. And this work is layered, it's complicated, and it involves a lot of effort. And so I have some stories to tell you, but I do not have any full answers for you. So we'll start by just talking about who teaches computation at the moment, at least as far as we can tell. So this was a project that I worked with AIP and some colleagues at AAPT on to distribute a survey across physics departments in the United States, and asked basically a lot of questions about teaching computation, personal beliefs around it, where it manifests in your department, what kinds of structures are available, etc. The way this was done is AAP actually does a really good job of this because they basically have every email address of every physics faculty member in the United States. And so what we did was we sampled about 357 departments. To give you a sense, there are about 760 departments in the United States that offer a bachelor's degree in physics. Now, this included a sample of two-year colleges, of which there's, I don't know, a lot more of those, right? So we sampled about a quarter of bachelor-serving departments, about that many. And within those departments, we just asked every faculty member who was teaching to respond to the survey, which is why we have about 1,300 folks responding. So AIP required us to have a preamble for our survey because nobody in the team could agree on what computation is. And if I asked every person in this room, I would get, I don't know, 57 different answers. So for the purposes of the survey, we took a very broad view, and I've given some examples here. But basically, let's just say this was a very inclusive view of what computation is. And so this tells us a little bit about what we think is maybe an upper bound on what we're seeing. Okay? So just some quick data before we actually do some modeling and characterize things, just really quickly here to give you a sense. So of the people sampled, about 75% say that they teach computation to undergraduates in some capacity. That doesn't necessarily mean courses, it could be research. We then sort of, within a department, we just decided whether there was a simple majority of the faculty responding in the affirmative, because it's hard when people disagree with each other in departments, well, for a variety of reasons, but they disagreed on a number of things. And so about 50% of departments we would characterize as teaching computation to students in some capacity. When we asked them about courses, again, looking at this sort of simple majority as the choice, about 25% or so of departments suggest they're teaching computation in introductory and advanced physics. That to us seems like there's a significant bias in the sample, because if you go around and you talk to people, it's really not that high. So there's a couple of things going on there. One is probably the definition is particularly inclusive, and two, who's going to respond to a survey about computational physics instruction? Computational physicists, right? So that's fair. That's a fair criticism. When we ask people about sort of where it shows up, right, people talk about homework and projects. They do not talk very much about interactive activities, which we would think of sort of as more evidence-based approaches, or sort of individual kinds of assessments. And so just really quickly, a majority of faculty report some experience teaching students computation. We do think it is actually more prevalent than it was in the past. There was a survey done now about 11 years ago that asked similar kinds of questions and probably is subject to the same biases as far as we can tell because of who they sampled and how they went about sampling. Here, the result was more like 10 or 11%. So even though I'm telling you it's sort of an upper limit, the upper limit seems to be changing, okay? We seem to be lacking formal computational physics programs. That's not a suggestion that we should have them. It's just a statement. 7% of departments report having a bachelor's degree in computational physics. And then there's a need for my field to sort of explore how to introduce these things with interactive methods and to develop assessment techniques. This assessment technique is going to be something that comes over and over again. Yeah, Greg?
Does that computational physics program include interdisciplinary programs for computer science or pure in-house physics programs that have computational?
I believe the question was worded was like, does your department offer a degree in computational, like a bachelor's degree in computational physics? And that would be where the 7% comes from. Yeah. Okay, but who teaches computation, right? So this is sort of also helping us understand that it might be computational physicists. So my student Nick looked at this problem because there's a lot of different questions and statements that we're using here that have a variety of different scales that people would respond to. What I mean there is that there could be like agree to disagree, there could be yes/no questions, there could be some numeric responses, etc. And traditionally educational data is not modeled well when you have these kinds of data as inputs. So Nick used a technique called random forest, which we've been using, and I can tell you about other work that we're doing around this, to sort of model these data. So here's some sample questions. I don't expect you to read them all, but they deal with lots of different kinds of things, right? So somebody may be responding to a question like, computational physics is hard to teach in the classroom. You know, how much do you endorse that statement? Computation can solve unsolvable analytical problems. There's no institutional support for me to teach it, so forth. My department considers computational instruction when hiring new faculty. We also have demographic information about the individual, and we have school information because AIP collects all of that information about the actual schools. And then we have things like, you know, when did somebody earn their PhD, et cetera, right? So again, do not expect you to read all of this. But here are all the factors that Nick used to determine whether somebody said that they taught computation or not, or had experience teaching computation or not. And you can see there's a lot of different factors. What he did was do basically a feature extraction and look at sort of the effect on the model over and over again, and able to sort of put some error bounds on this. What he found was that there are really only 5 meaningful factors in his model. That somebody reports or endorses that they use computation in research with their students, that they don't personally use it. That's actually a negative predictor. The details of the model and why that's positive we don't need to get into, but basically looks at the change in the error. These 2 are interesting. The computation allows me to bring in new physics or bring in new problems into the classroom, or the highest degree offered. And that's actually basically whether they're a 2-year college or not. Okay? Ooh. So, uh-oh. Did you steal that computer? You're okay. So we wanted to look at whether these factors actually made sense or not. So because there were so many of them, we could have, look at this, but we wanted to understand, are we actually seeing the sort of general trends, right? And it turns out we are. So, if somebody's responding to, I use computation to provide research experiences, they're more likely to use it in the classroom. If they think it allows them to bring in new physics, they're, again, more likely to bring it in the classroom. Things like gender, race, the type of school beyond 2-year college, whether it's a HBCU, Hispanic serving, none of those factors actually mattered in the model. Yes, please.
This is a lot of surveys about what the faculty is teaching. Ask students who graduate what they learn.
Yeah, that's a great question. So we'll get into student learning here in a second. But yes, it is very difficult to do a national survey of students. But also an excellent question for my next NSF grad. Thank you. I should write that down because I'm going to forget it. So things like this, the undergraduate program, my department values instructing. So anything that's stated about the department or the institution, whether it's resources or values, things that we often think of as levers for change, didn't have much of a impact on the model at all. So what Nick argues in the paper is that faculty who teach computation tend to use it in research or in some other way. They believe that it brings in new physics and new problems. They teach at institutions that offer at least a bachelor's degree. And these departmental and institutional levers don't seem to matter because faculty, at least those who responded to our survey, treat it as an individual choice. It's something that they're doing, which again sort of leads us to believe that the folks that are responding to it are of a particular subset. So a lot of open questions here. How might we support more people doing this instruction if we're seeing the same kinds of folks? What can departments do? Are there actual levers here? Is this a bias in the survey? Is this something that we really do have, do department chairs and deans actually have levers here they can use? And how do we help faculty design courses, curriculum that actually teach this stuff effectively? And I think this starts to go to your question, but it'll maybe unpack it. And please dive in again if I don't get to it in a few minutes, okay? So we have this workshop that we offer the faculty. It's the Partnership for Integrating Computation in Undergraduate Physics. This is from this past year where we had basically this many minus 10 or so folks from across the country learning how to integrate computation, how to teach their students how to sort of assess it as best we can at the moment, and so forth. This organization has a pretty substantial group of workshop participants over the last 4 years. This is just a dot for every institution that has sent people to it, and you can see they're kind of all over the place. This group also develops activities for people to use. If you're curious, you can go to gopickup.org and check out some of these activities. So this is one developed by a colleague of mine, Ernie Behringer, who's at Eastern Michigan University. And this is an analysis of a 3-bar pendulum. There's some learning goals. There's basically information for the folks to decide how they are or not going to use it. This organization's grown quite a bit. I'm just showing you a couple of quick things here. So this is the number of verified educators, people who actually are using and downloading materials. You can see there's been pretty significant growth over the last few years. We also have a Slack team. If you're interested in being invited to that, let me know. And this is sort of for communication and sharing of ideas, and that also has continued to grow. If we look at the number of people that are actually on the website downloading materials, there's substantially more of them across the US, and it's actually sort of international. There are people kind of all over the place that are downloading and using these materials. And so in working with this group for a long period of time, right, these are sort of faculty who are not education specialists. They're just interested in incorporating computation. I've heard a lot of different kinds of questions. So how do we integrate it across the department? What do I have to give up to do this? How do I know what my students are learning? What is the best format to teach it? How do I teach TAs? How do I help my colleagues, et cetera, et cetera? And these actually form a lot of the kinds of questions that we ask in our research group, right? Because our idea is to sort of integrate this and help support people in their integration of computation. And so much of our research is informed by just talking to people. So I'll tell you a little story about how you might go about doing this, right? So this is what we've done at State. First of all, your mileage may vary. Your institution is different from mine. So, please feel free to ask questions. So I'm at a research-intensive university. That means there's some significant challenges to doing this work. One is resourcing. Our service courses make tons of money for the department. They're big. They have lots of students in them. And they are significantly understaffed, which means that we make a lot of money on them, right? So the courses are taught at scale. Not only those courses, but actually also the larger courses. The changes that we make need to scale. We teach about 1,000 students per intro course. That's like Introductory Mechanics for Engineers has 1,000 students in it. There's about 100 students in the advanced courses at any one time, somewhere between 50 and 100, depending on which course it is. There's a high research demand. Investment varies widely. A lot of the instruction is done by TAs and LAs. And we have a large, diverse faculty, which means that big changes require a lot of discussion. But there are some positive things about this. We had a supportive administration, or we have one. The dean, the chair, the undergrad chair, they're all supportive of making these changes. Those research demands are actually positive because we have an education research group, and educational transformation grants count for people. So that means that we can get external money to support certain kinds of changes. We also, again, have this large, diverse faculty. We have a lot of progressive junior and mid-career faculty that care a lot about community. They care a lot about graduate students and undergraduate welfare. And so there's a lot of push to do this, not just within computation, but more broadly. And we've had a lot of people that are computational physics hires. So there's a lot of people that want to see this happen. And then we're a big state school like this one is. We had some state level investment. We have a new STEM teaching building. And to get into that building as a department, we had to argue that we were going to make changes to our teaching. And now we get 3 rooms, big rooms, that are slotted to us because we made these changes. And nobody wants to give those rooms up because giving up space is like giving up money at a university. You just don't do it. So here's what our physics major program looks like. So students take intro mechanics, E&M. I'll tell you about this course, CMSE 201, modern physics, class mech, et cetera, et cetera. That's the typical progression. What you're going to see here is some colored boxes that tell you about when we've started to do this kind of work. So yellow is like people are using computing for mainly plotting and maybe some algebra. Light green is some of the sections have computational instruction. Dark green is there's kind of full integration of computation. Black is when the course isn't offered because some courses are offered every year. Okay? So let's start at the beginning of time when I started at MSU because that makes sense. So in the spring of 2014, we got funding to develop an intro mechanics course with computation. And so you can see there are some sections of that intro course that were altered to have computation. There's some crosstalk between folks here and these courses, and they start using some tools to do some plotting mostly and a little bit of algebra. About 2 years later, the department formed a committee. My department does everything by committee. There's at least 3 layers of bureaucracy between you and any change you want to make. One is the ad hoc committee that investigates the problem. The next one is the actual committee that's responsible for the ad hoc committee, and then there's the advisory committee to the chair, and then it goes to the faculty. And by that time, you've talked to everybody. So we formed this department committee to investigate integrating computation. We got funding for an intro E&M course, and this department of computational math, science, and engineering starts up. This is a cross-college department that is focused entirely on computational science, data science, et cetera. So you can see the mechanics course, people keep taking it. The CMSE course, some of our students start taking it. The E&M course becomes the pilot course with computational instruction in it. And then after a year's worth of the committee vote and going through all these layers of bureaucracy, it goes to a faculty vote. And there's a unanimous vote in support of integrating computation in our major sequence over 5 years. And we will require this CMSE 201 course. before students get to classical mechanics. So there's some more crosstalk here. Then all of our students have to take this course. We've started to integrate it in classical mechanics, right? StatMech starts to use some plotting. The E&M courses, so you start to see like major changes begin to happen. This is basically where we are now. And so just to show you, like, these are the physics education research faculty that sort of worked on these projects. You can see that the intro courses have basically been turned over to the faculty. Some courses had absolutely no physics education research faculty involved at all, other than in discussions. And this is me, because I've been teaching E&M for a while. But now we are basically getting to the point where in the fall of 2021, we're going to be in this new STEM building. We are planning to have all the introductory courses transformed because we're going to be in that new building, and all of those courses will have computation, and we will see if we can sort of deal with the issues of quantum. Okay? So what was critical to us was this sort of external support that sort of accelerated the changes, right? So this is CMSE 201. It's actually an introductory course in computational modeling. It's purely focused on that. So this is taken by STEM majors. It only has a Calculus 1 prerequisite, and it's required for our majors now. And so the students work in these groups. They're taught in about 50 to 70 student sections, so they interact with each other. It uses pre-class assignments and videos and small programming assignments in sort of a flipped model. So students do a little bit of work outside of class, and they come in to do sort of their big project. There's a paper, I believe it's actually been published, but I can give you the details of it, that describes the course. Here's what it actually looks like. So it's taught in a kind of a new space. So there's 5 students in a group. And they all have laptops out. They're all working on the same activity. People are sort of sharing that activity out here. You can see that model. Here, this is the instructor here, this is Mike, so he's teaching this group here. Actually, this whole table, 1, 2, 3, 4, these are all physics majors. I don't know about this one back here, but these are all physics majors taking that. So here's typically what they would do. They'd have some sort of in-class assignment with some goals, right? By the end of this assignment, you should be able to use functions, use loops, use matplotlib, etc. And they're modeling the motion of a skydiver. This actually is, I think, the day 8, so that would be like their 3rd week of class. They're doing some Jupyter Notebook analysis of a skydiver. And then there's some additional activities, air resistance, opening a parachute, etc. So that's been critical for us because it's required before class mech. And so it allows us to leverage that expertise in other courses. So, all right. So to the question that was asked, right? We can do all of these things, but what are students actually learning? Right? Can we sort of identify that? Can we sort of make sense of it? And can we unpack it? So I'm going to quickly tell you a story. So in our introductory courses, we use minimally working programs. So this is basically a Python model of the orbit of a satellite around the Earth. Okay? And there's a lot of stuff missing. So the way that this model works is basically it creates the Earth, and it creates a satellite, and the satellite moves straight by, not interacting with the Earth. And students are meant to identify what's going on here and to build a program that actually creates a geosynchronous orbit. So after 2 hours worth of work, they have done the following. They have made changes to the initial conditions. They have constructed appropriate model parameters. They have built the force, and they have done the integration associated with that particular force, right? And so all of the students that we have in our courses, and when we did this at Georgia Tech, are leaving with this correct piece of code at the end of their class period, okay? What we did at Tech is we had them then use that work on their homework every week. So they did a model every single week. And then we said, okay, well, can we then see if they can do this by themselves, right? Without the help of the TA, without the help of their classmates. So we gave them a new activity where they had to do this kind of work, assign initial conditions, et cetera. And we find that about 60% of students could do this without any sort of support, right? They're just doing it by themselves. This is particularly interesting, I think, to me, because these students had no prior experience with computational modeling, and only about 10% of the students had any experience with computer science before doing this assessment. And they are sort of, that's not a factor in the result here, as it turns out. What we were very curious about were the students that made some sorts of mistakes. And it turns out that there's exactly 112 different ways that students could go wrong. So we went through and we looked at every single piece of code and classified the kind of mistakes that we saw in every piece of code to understand, well, what are the sort of common things that we see? Using a technique called cluster analysis, which allows us to sort of reduce that space from 112 different ways to just a few sort of common ways, we found that most students fell into just 5 clusters. The main issue with their code was a sign error in their force calculation, which for a central force is a huge problem because it blows up, right? That's an enormous problem. Turns out that a very large number of students actually had completely running code, but they made a typo in the initial conditions. And because you're producing a nonlinear model, that gives you a result that's wrong, and the homework system tells you it's wrong. 2 groups of students treating forces like vectors in an incorrect way, either as a scalar or raising them to a power. Python actually tells you you're being naughty, but if you can't parse the error message, you might not know what to do, and you turn in the project anyway. And then some students calculate the force outside the loop. In this paper, we actually argued that the dominant errors were not syntactic, that they didn't have to do with students' understanding of syntax. Many years later, I'm a much older and wiser person than I was. And I don't think we can actually separate these things anymore, because the way that knowledge seems to work is that people blend their knowledge from different spaces. So if I'm engaged in an activity around computational modeling, in physics, I might be blending my physics knowledge, my math knowledge, and my computational knowledge to engage in this sort of more complex practice. And so it might not be able to say, like, it's not the syntax. It could be my understanding of the syntax in this context that is the challenge. And I can't answer that question at the moment. Please.
So among those students who were able to finish successfully, were they able to solve these things analytically as well?
No, that we did not test whether they could solve these things analytically as well in this study.
Right.
Is
it solvable? I mean, at this level.
I'm
not doing the two-body problem.
They're not doing the two-body problem, but this
Is it solvable?
It is, but this is an introductory mechanics course for engineers. We would not have asked them to do that analytically.
So everything was done numerically?
Everything was done numerically. That is correct. Yes. Yeah. OK. All right. A lot of open questions here, right? How do students go about constructing these programs, right? There's some issues here, because I can answer the question, well, there are challenges, but where do those challenges stem from, right? What kind of knowledge and ideas are students blending when they're engaged in this work? What kind of patterns of participation do we begin to see when students are doing this? What forms of instruction can support different learning outcomes, right? These are still questions that are actually being asked by folks in the pickup group. I'm going to sort of switch gears here and tell you a little bit about different forms of instruction, in particular about TAs, because computational instruction can look like a wide variety of situations. And we've begun to pilot a different approach at Michigan State using these sort of problem-based approach, where we don't necessarily give students a lot of scaffolding as written materials, but rather we give them a lot of scaffolding outside of the class and then through tutor interactions. So this is a course that we teach. This is our introductory course for engineers, where students have to do an analysis to find essentially the velocity that they need to construct a geosynchronous orbit. Now, that's not really what this says. There's a lot of words here about being an engineer and so forth. They have to kind of figure out what they're supposed to do. The next day they come in, and the person who is, this is Elliot Carver. Does anybody watch James Bond? There's a whole lot of James Bond stuff in this for some reason, and I don't know why. I think one of our TAs was really obsessed with it the semester we wrote these problems. So basically, once they've completed the work on the first day, they come in the second day and they're asked to make a simulation because they have to make it for a presentation. And so they're given this same piece of code that I showed you a minute ago. It looks like this, and they're asked to make that model, right? And so it's similar kind of process, but the pedagogical structure is a bit different. And at Michigan State, we have a much larger student population taking our introductory physics courses and much fewer resources for that. So we use learning assistants who are undergraduates who've taken the course in the past. They come and they facilitate student learning in the classroom. This is Katie. Katie was a physics teacher in this class for 7 semesters, which means she has 7 semesters more of instructional experience than the most recent hire we had at Michigan State. So these students are really good. They're really good at teaching physics, and most of them are not physics majors. They understand sort of what the students are going through. They understand how challenging the class is, and they understand how to help support them in doing this work. What we were curious about was, how do they go about teaching these computational problems? What are the things that they do around this? And can we understand, sort of from their perspective, why they go about doing the things that they do? So there's a lot of details in the paper here that I'll sort of gloss over. But basically, one of my students, Alana, did a bunch of interviews with these learning assistants and looked for certain kinds of themes around their instruction. What she found is that they talked a lot about the utility of computation, their own perceptions of how useful it was, and they wanted to sort of convey that to their students. What kind of outcome they were trying to get out through their instruction, basically they want their students to take away from the problems. Something that they tried to moderate, basically something that was going on within the group or something that helped them sort of get to an endpoint in the class. So this could be things like students' frustration. It could be things like time, right? Things that they were just trying to like pay attention to. And then the teaching strategies that they use, what they actually do for their instruction. So this is a very educational heavy paper, right? But basically, what you look for is variations across these themes. So for example, in teaching strategy, a TA or an LA might be focused on helping the students navigate programming errors. Like that might be the main thing that they're focused on, is getting them through that programming error. Another strategy might be like leveraging the affordances of computational problems to sort of illustrate conceptual understanding, right? Like what kinds of concepts are you actually exploring with this problem, and so forth. So, and leveraging collaboration is sort of a big one, right? Like, I'm not going to tell you what to do, but you talk to each other in your groups and figure out what you're going to do. And then what you do is construct what's called the category of description, basically saying like this is the kind of way that an LA might canonically approach their instruction. It's not the way that this LA does it, but it's sort of a coherent argument for what these sort of hang together. So if I am an LA who thinks programming is a very important skill, I might be really focused on teaching students programming skills. Therefore, I moderate the work pace. I try to make sure that they get through all of the activities with all of the programming and help them sort of navigate those programming errors, because I want them to do all of the programming in that 2-hour block. Okay? Here's some quick data on this. So this is all done through interviews, and it's sort of an interpretive analysis. So here's Kendra, who's one of the LAs. This is a pseudonym. We don't have an LA named Kendra. Most of the time, I just teach them how to do it, because it's usually when they've just edited like one line of code, and then it's like, oh, we have a tabbing error. I'll just be like, oh, here's how you solve that. Highlight and do the thing, and then, yeah, it's good. And then they'll be like, OK, right? So that's really Kendra expressing like how to get students past a programming error, right? Just show them how to do it, and then move on. Whereas Molly, sort of answering the same kind of question, is saying, I might say something like, ask somebody, ask the group, what are they doing? And if someone responds and it looks like the other two aren't paying attention, I might ask, oh, are you guys good with that? Are you guys on the same page? Do you guys understand that? Or something like that. So Molly is leveraging the collaborative aspect of the environment to have the students answer each other's questions, as opposed to just navigating those programming errors. Now, these show up in a variety of students. Like, they don't just do one thing, right? Let me make that clear. So what Alana was able to do is to sort of categorize 4 clear ways that we might see LAs doing our instruction in this course. One is sort of focusing on just programming. Another might be learning the conceptual physics via computation, that's like an affordance of computation. The third is that computation can be a tool for doing physics, for gaining a deeper understanding. And finally, that we could shift students' perception of what it means to learn and understand physics through computation. And arguably, these might be seen as sort of increasing levels of teaching sophistication. And if you talk to the people who designed this course, their goals are really that students leave the course with these kinds of ideas about computation, that it's a tool for doing physics generally, and that it can ask and answer many, many new kinds of questions, and not necessarily these. So a lot of different open questions for us here. How do different instructional approaches lead to different outcomes, right? If I take a particular kind of approach, does that lead to certain kinds of learning outcomes? Do these things change over time? They're probably not static. There's certainly some dynamics here, especially if you have more and more teaching experiences. How might we actually support the instructional approaches that lead to the learning we want to see, right? It's not necessarily that these two things are not disconnected. They are connected together, and sort of understanding how that connection works is important. And how does this work apply to faculty and grad students? We only worked with learning assistants, right? Faculty and grad students have much more experience with physics than undergraduates do in different kinds of contexts. So it could be that these are not necessarily the same kinds of things. All right? So these are some stories about all of the work that we do around computation. There's lots of other stories I could have told you, but I didn't. So there's a lot of different people that are doing work in the lab. You know, how do students debug a program with a visually incorrect result? What challenges do faculty encounter when they attempt to integrate computation? How do high school teachers attend to equitable participation in computational activities? You know, how do high school teachers change their practice when teaching computation, et cetera? So there's a lot of work that's going on in the lab. And basically our work is trying to support this integration of computation through research with students, research on activities, pedagogy, curricula, with faculty, and with departments in larger systems. And this research is sort of helpful in the sense that it helps us design the structures that are necessary to see this happen. So I want to go back to this real quick because the work that I do is research that can support education. A lot of that is informed by the history that I've had, but a lot of it is actually supported by the community that I get to work with every day. So I want to show you pictures of them because they're really important to me. So this is them. Thanks.
So evidently it was an accomplishment to get that course, CME 201, into your curriculum.
Yes.
And someone had to do that.
Yes.
So I have two questions about it.
Yeah.
First, how did you do it?
Yes.
Or how did someone do it when there's all this struggle over what a curriculum should be? Second, how did anybody settle on the language?
Yeah.
And what we faced, I've been on a committee in this department. There's so many languages, and you never know what you're doing.
Right.
If we teach a course ourselves, we could force a particular language.
Yeah.
Is that a good choice?
Yeah.
What should we do? How do you settle those two issues?
Let me answer your second question first, because I think it's a little bit easier. So the CMSE course is taught with Jupyter Notebooks and Python. And so the argument that was made in that committee and went up through these committee chains, right? That's a big part of our, which is a big part of the answer to the first question, was that, hey, they are using this stuff. They are doing it well. We should leverage that expertise as we go along. And we can talk about, in advanced courses, doing something different. But for the sort of core courses, we have this sort of support structure that's already put in place if we require this course. So that was the main argument, and it was an argument that people were happy to buy, to say like, oh, some other department is already spending an entire semester teaching them how to use this tool. We should just leverage that. Then we don't have to deal with the issues of installation. We don't have to deal with the basic syntax issues. We could focus on teaching the relevant physics in that course. The answer to the first question is that it went through this committee structure, right? So we have a group of people that were really interested in trying to do this work. And so they worked closely with CMSE. In fact, we had a member of the CMSE department on the ad hoc committee. And then that gets reported to the undergraduate program committee, so forth and so forth. And our department has a culture of trusting that committee structure. So by the time it gets to the full faculty vote, a lot of these issues have been aired in each of the committees along the way. Now, that's not the culture everywhere, but that's our culture, is to sort of trust that along the way.
So I've seen this kind of example before that I for Python many years ago.
Yeah.
But that particular example of the satellite, I look at it from the perspective of teaching computational physics at a higher level. And
Yeah.
say, oh, he's teaching the Euler method and he hasn't got any uncertainties. I guess you don't focus at all on the numerical analysis aspect?
Yeah, so the question was, the example that I showed doesn't have the details of sort of issues with error and the numerical analysis that's necessary to understand the nature of the model, right? And the answer to, well, it wasn't the question, that was sort of a statement, and then I think the question was why not, right? Or why are we doing it that way?
Do they get access to that?
Yes. So the answer to the question of why is because we're sort of focused on treating just models in general at the moment, right? So can you use this as a tool to understand physics sort of more generally? And so we have not emphasized the issues of that you see in numerical analysis in those introductory courses. They do see that later on. So we have a computational physics course that then leverages sort of all of those experiences to say, okay, now that you've done all of this work and sort of you understand how to build these simple structures, let's understand the details of, you know, how good is this model, right? And so it's sort of at the end point. That's a decision we made to say we're going to build on all that and then sort of unpack the details by sort of correcting it. Yes, sir.
So with the schedule you showed early on, it started off the very beginning. First introduction was just in like first semester intro to physics.
Yes, sir.
And considering, assuming it's sort of like at our university, considering there's a whole lot of non-major students, like 1,000 people
Yeah.
in the intro and then down to 100 later.
Yeah.
If this is, maybe this is sort of the wrong idea, but if this is ultimately about teaching physics majors how to program, why was it started on so early when you're spending a lot of time on non-physics? That's
Right.
sort of maybe a negative way to put it.
No. Your question is very good. It's very good. Yeah. Why integrate in the intro course really at all, right? If the purpose seems to be focused on physics majors, right? Why not just start with CMSE 201 and the answer is that you know, physics it has this sort of three pieces to it, right? The theory, the experiment, the computation. And so our department has decided to represent all three of those when it's being taught in the introductory course. Sort of in addition to that, there is a significant effort in the life sciences to make biology more quantitative.
So it's suiting everyone's needs.
Yeah, and the issue with quantitative biology is that quantitative biology immediately becomes incredibly complex and hard, which is why it's not quantitative in the introductory sequence, right? The nice thing about computational modeling is that sort of agentic models and things like that can help you understand and unpack issues of quantitative biology in ways that are more simplistic than we could in the past, right? And so, yeah, potentially in the future, is serving a variety of needs, but we're sort of laying the groundwork for it. Yeah, Daniel.
Yeah, you have been preparing this program for several years, and can you tell us what is the response of these students? Is there like, at the beginning probably they were not very pleased with all these changes?
I can tell you from,
because, you know,
yeah.
if you want to do something like that, you know, the first thing is that, you know, if you want to encourage like faculty to do it,
Right.
That's also kind of risky, right? To introduce something, because the student evaluations maybe.
Right.
So can you tell us how this was progressing?
Yeah, I can tell you two quick stories. So one is a survey of physics and astrophysics majors around computation. And one of I don't have the slide here, but I have it somewhere. Would basically, if you ask physics and astrophysics majors, you know, is computation important to your professional development, right? Computation defined in a particular way. What you find is about 90 to 95% of them say it's important or it's really important, right? So there's this sort of recognition among students that this is something that, like, I'm going to need in the future, right? That's one data point. The other data point I'll give you is actually here. So I taught this course. You could see here that only some students took 201. I actually didn't have those students because this is about almost 2 years of a gap. I now have those students, or actually probably these students in this class, the one that I'm teaching this year now. At this point, I was spending probably in the first 2 weeks, 10 hours a week debugging Python installations that students had and helping them with syntactic issues on the first homework assignment, which was make a plot, right, of some function. Now I don't do any of that. The other thing I forget who I was talking to, but I asked them to do computational homework activities every week and turn them in as homework. And I need to look at this data, but my memory of it is that around this time, only about 30 or 40% of students actually bothered to even turn in those activities. And now it's closer to 90%, right? And so that might be of effect of a lot of different things. I suspect it's really the sort of preparation of the sort of basic stuff, right? Like, I don't think I'm challenging them anymore with the activities that I have. Yeah.
So I'm not sure how well Jupyter works with this, but do you also teach version control stuff in these courses?
Not in, so I teach it in this course, ENM2, which is an optional course for physics majors. They have a computational project. So this course is actually a project-based course. It's not taught in a lecture style. So they build a computational project over the course of the semester, and they use GitHub for that. The follow-on course to this course, the CMST 202, actually teaches them GitHub from sort of like a data science perspective, right? Like they actually have to do all of the checking in. They have an exam on it and stuff like that. So, and about 25% of the students that take CMST 201 take 202. Yeah, Greg.
Is the model for the students getting access to computers that you have computer labs with pre-installed distributions of Python? Or is it most students have figured out by at least at this point in your program how to install it on their own machines with their all different operating systems?
Yeah, so that's a good question. So 201 requires that they bring a computing device that can install Anaconda to the class. Like that's a prerequisite for enrolling in the course. Like you would not be able to participate in the class without a laptop that can install Anaconda.
Are there issues with students who can't afford laptops?
Yeah, so that's a great question. Our library allows students to check out laptops with sort of a standard install, which includes these sort of computing devices. The engineering department, college, I believe, also does the same. I would have to talk to Devin, who's like the coordinator for 201, to ask if that's like how big of an issue that is. There are places to access it, but yeah, I can see the issue, and I don't actually know the answer.
We have students with desktops and no laptops. I've had students with desktops and no laptops.
Yeah.
So it's really hard for them to bring into class. They can't afford a second computer.
No, that's fair. Yeah, so yeah, so our I believe our institution requires students to have a computing device, but I don't think that means laptop or even a computer. I think in some cases it can mean a tablet. And also like that's a requirement, right? So yeah.
This question, what has happened with integration and application of the graduate courses?
Oh, that's a good question. So in the astrophysics courses, I believe there's been more take-up. In the regular physics lecture courses, I don't believe there's been any.
Was that influenced by what you all did in the graduate program?
No, so that's an interesting question. So the people who tend to teach the graduate courses at MSU tend to really only teach the graduate courses. So there's often not a lot of crosstalk between the folks that are teaching the undergraduate courses and the graduate courses. I don't know the historical background of that, but there's not a lot of crosstalk from what I can tell. No.
Any other questions? If not, let's thank our speaker again.